Hello, my name is Ayosha Hermann. I work at the Professorship of Sport Equipment and Materials at the Technical University of Munich in Germany. In this short video, I want to present a study in which we investigated the ability of two different flexible sensor principles to measure the knee flexion angle in an alpine skiing setting. The study is published in the Journal of Sports Engineering. My co-authors are Julius Osterhild, Yakira Mirabito, Nicole Bauer, and Veit Zenner. The motivation for the study comes from our research concerning knee injuries in alpine skiing. Knee injuries are the most common injury in alpine skiing, and nearly half of overall injuries concern the knee. The existing safety device is a poor mechanical ski binding, which was designed to prevent tibia breakages, but is not successful in preventing knee injuries. To address this problem, we work on a research project to reduce these knee injuries and develop a mechatronic ski binding. As in our opinion, the mechatronic ski binding is the most promising concept towards this goal. A mechatronic ski binding is a safety device which supervises critical parameters using sensors. This can be the knee flexion angle, the muscle activation of the thigh, the loads at the feet, and the speed of the skier. Based on knowledge about the injury mechanisms, these sensor values can be attributed to a risk of injury, which leads to an adoption of the binding settings. The study presented here focuses on one of these parameters we want to be supervised by the mechatronic ski binding, which is the knee flexion angle. Examples of critical situations with respect to the knee flexion angle are situations where the knee is not flexed at all, meaning a straight leg, and situations with the knee in deep flexion. In both cases, the anterior cruciate ligament is under high load, and small external forces can lead to an injury or rupture of the ligament. If the information about the flexion state of the knee would be available in such a situation, a mechatronic system could react accordingly. Commonly used measurement technologies to measure body angles are, for example, camera-based motion tracking systems, inertial sensor systems, known as EMU sensor systems, or goniometers integrated in an orthesis or similar. For the use in a mechatronic ski binding, these methodologies have disadvantages, like a camera is limited on a spatial area, EMU systems available are complex and expensive and tend to drift in the signal, and standard goniometers have a stiff component, which could be an injury risk. Therefore, we wanted to investigate if flexible silicon-based sensors can be used to measure the knee flexion angle when integrated in skiing underwear. A silicon-based piezoresistive sensor fiber and a capacitive silicon sensor were compared with respect to their ability to measure the knee flexion angle. Each sensor type was incorporated in base layer compression pens. These sensor underwear systems were validated using a flexion test rig and in a human subject test. The piezoresistive sensor system was custom-made to allow perfect integration of the sensor fiber in the textile. As you can see, the textile has some tunnels in which the fiber could be implemented. The capacitive sensor system consists of a commercial compression garment with the capacitive sensor sewn over the knee region. For the validation test, single leg prototypes were used. On a knee flexion test rig, the prototype was tested for functionality. The custom-made test rig consists of an upper leg and a lower leg made of silicon connected by a hinge joint. A pneumatic cylinder powered flexion and extension movement in the range of 0 to 60 degrees. The velocity of the flexion extension movement was varied by controlling the air pressure that supplies the cylinder. A rotary sensor with an accuracy of 0.1 degree was used to record the amplitude and velocity of the movements of the test rig. The behavior of maximum and minimum flexion values of the long-term tests are shown in these figures. A relaxation of the resistive sensor signal over 3 hours of 40 degrees for the maximum values and 20 degrees for the minimum values was observed. No large displacement of the prototype relative to the leg surrogate was observed during the measurement, which could have explained this relaxation. The capacitive sensor system showed close to no relaxation during the 3-hour test. The resistive sensor system was sensitive to velocity of the flexion extension movement. The sensor signal drifted to higher values for higher velocities. Their influence was greater for smaller flexion angles, like smaller than 30 degrees. The velocity dependence for the capacitive sensor system was smaller than for the resistive sensor systems. 20 participants, 7 male and 13 females, with a mean age of 23 plus minus 6 years, with no self-reported injuries and a high fitness level, performed flexion extension movements wearing both prototypes. For the resistive sensor system, only the knee part of the pants was used. The participants were asked to stand in the ski binding on a platform with an inclination of 15 degrees, wearing the same ski boot model in their respective shoe size. This setup was chosen to simulate ski-like flexion behavior and to represent the fixation of the angle by the ski boot. The maximal and minimal values of the first flexion were used to calibrate the respective system. Camera-based automatic 2D motion tracking was used as a reference system. Before the start of the measurement, the participants were asked to perform 2 squats so the pants and sensors could align. At the start of the measurement, the participants were asked to flex the knee as deep as they voluntarily could, which was about 120 degrees, followed by 10 squats to about 16-degree knee flexion angle. A metronome of 50 beats per minute gave an orientation for the speed of the flexion for these 10 squats. Blunt-Altman plots were used to compare elongation sensor and camera systems results over the whole range of the knee flexion angle. Exemplary results for a male participant are shown here for both systems after the knee angle calculation using a 2-point calibration. It is clearly observable that the two systems have a different behavior. For example, the piezoresistive sensor is constantly overestimating the knee flexion angle by 12 degrees plus minus 7.5 degrees. The capacitive sensor shows superior behavior with a mean deviation of minus 3.3 degrees plus minus 5.6 degrees. Whereas in the flexion movement, the knee flexion angle is overestimated, and in the extension movement, the knee flexion angle is underestimated. Across all tests and participants by sensor type, the mean deviation between sensor and camera system was 10.6 plus minus 7.5 degrees for the resistive sensor system and 3.4 plus minus 5.1 degree for the capacitive sensor system. The mean R square across all participants is 0.92 for the resistive prototype and 0.97 for the capacitive prototype. When discussing the results, we can say that capacitive sensors provide better results than piezoresistive sensors when used to measure the knee flexion angle in a skiing situation. As the capacitive sensors show less drift, have less hysteresis, and are less influenced by the environment. On the other hand, piezoresistive sensors are easier to use and integrate in a textile system, and the electronics are less complex. Therefore, the measurement principle would be interesting for a commercialization of such a system. To allow such commercialization and modeling of the sensor characteristics may allow to correct the sensor data. A key aspect to achieve valuable data is the calibration process. The 2-point calibration used in this study may be unhandy in a real-world scenario, and other calibration procedures should be found. A possible one could be a dynamic calibration, where the full range of flexion is recorded once at the beginning of the skiing day, and the relative flexion is recorded throughout the day. In this study, the influence of rotation movements and the abduction and adduction movements were not recorded, and the influence is therefore unclear. A promising solution for a future wearable system could be to combine multiple measurement principles. For example, a hybrid sensor system consisting of IMU sensors and a capacitive sensor could be merged using a Kalman filter. This could allow to correct the drift by the EMU sensor. With this idea, I would like to finish this short presentation and thank for attending and listening and your interest. If you are interested in our research on this topic, please don't hesitate to contact me using the contact details shown here. I wish you a safe skiing day the next time you can find time to be on the slope.